Look at example A. The graph below shows two functions, college enrollment and university enrollment. On the same grid, do total enrollment. So in 2004, there was just over 6 million people in college, just over 10 million people in university. How many in both? Just over 16 million. So I'll do this in green. I would put a dot about there. Can you see with that dot that your x value is not changing because it's still 2004, but your y value is changing because you have to add both of them together? And so when adding graphs, here if we look in 2005, just over 6 million, 10.5 million, so we would probably be around 16.5 million. In 2006, again, just over 6 million, almost 11 million, so we'd be really close to 17 million. 2007, looks like there's enough to be just over and in 2008, over 6 million, over 11 million. If we join the graph as well, this is what it would look like if we were adding graphs. So if we had to summarize what we just noticed, all we did was add the y values. The x values stay the same. Look at your specific y values. Add them together. Example B. Whoops. In example B, they give us a formula. The stopping distance for a car is a function of the speed of the car when the brakes are applied. So your stopping distance is your time that it takes to react. Then you slam on your brakes and your car skids forward, right? So usually that reaction time, you would want that to be quick, right? Oh, there's a puppy in front of my car. Isn't that nice? What should I do? No, you should be like, the reaction time hopefully is short. Like, ah, puppy, brakes, right? Instead of, oh, look at the cute puppy. Okay, so we do have a bit of time that it takes to react. That reaction time is blue. Okay, the reaction time distance is blue. I'm going to put a blue box around that so you can see that in the blue graph. Okay, your reaction time is probably the same, but your reaction time distance is going to be different. If you're going 100 kilometers an hour and you see that puppy, and if it takes you even a millisecond to react, you're going to travel a farther at 100 kilometers per hour in a millisecond than you will if you're traveling 1 kilometer per hour and you react within a millisecond. Okay? If we look at our blue graph, here we have this point where you're not going any speed. Okay? And you see the puppy and go, ah! Okay, but you're because you're not traveling anywhere, you won't go anywhere with your reaction anyways. Okay? You maybe should look into some help if you're reacting when your car is stopped anyways. Okay? Now, your stopping distance is the red graph, which is right here. Your stopping distance is from the moment you see and react, then slam on your brakes and slide forward to the total time that it takes you to stop. So obviously, the faster that you're going, the farther it's going to take before you actually stop compared to if you're not moving at all. Now, if I want to graph my braking distance in green, can you see that you could rearrange this equation? I'm going to call braking distance B. If I wanted to get B by itself, I would have to take my red graph, which is my stopping distance, and then subtract my reaction time distance. So the reason I took some time to look at this is because now what we want to do, if we want to graph the green graph, we want to take the red graph and subtract the blue graph. And that will tell us how far we actually skid before we stop. So if we take 100 kilometers per hour, right, it took us 90 meters to stop completely. We traveled 20 meters during our reaction. Does it make sense that your braking distance was 70? So if it took 90 meters to stop completely, is that better now? Okay. And if we take a couple other points on here, and again, they don't necessarily line up nicely, but you can sort of estimate. It looks like here I have 58 minus 16. 58 minus 16 would be around 42. Take another point here. I've got 20 minus 8 would be around 12. 0 minus 0 would be 0. I love that situation, right? Your car is stopped. The puppy runs out. You go, ah, puppy. You don't travel at any distance while you react, but you still slam on the brakes and don't travel any distance till you stop. And so we can draw our graph here in between. That would be our braking distance. So just like adding, if we wanted to summarize subtracting graphs, your x values stay the same, and you just subtract your y values. So far, adding, subtracting doesn't seem too bad for working with graphs. In our third example, they didn't even make up an example, a word problem to make it fit. We just have two graphs, and it says you've got your red graph f of x and your blue graph g of x, and we want to graph f of x times g of x. So what we're looking at here is multiplying graphs. What do you think is going to happen? We multiply the y values, right? Adding graphs, we added the y values. Subtracting graphs, we subtracted the y values. Multiplying graphs, we multiply the y values. Isn't it nice when what seems logical is actually what happens? It seems like it's getting rarer and rarer as you go on. Okay? Now, so I can take a point, but things get a little complicated here with these graphs, because if I pick one point on one graph, well then multiplying on the other graph, I might have decimals, right? Things might not work out nicely. So one of the things with multiplying graphs is you start to look for what are some easy points to multiply. 0 is easy, because 0 times anything is going to be 0. So you can look on your graph and say, where is my red graph 0? My red graph is 0 right here. It wouldn't matter what the blue graph is. The blue graph happens to be 0 as well. But it wouldn't matter what the blue graph is, because 0 times anything is 0. So if I look at all the places where my red graph is 0, I get that point. If I do all the places where my blue graph is 0, at 2, my blue graph is 0, and 0 times looks like 1.482. would still be 0. 0 times 1.482 is still 0, so we would have those points. Points where y equals 0 are easy. What other things are you really good at multiplying by? 1. Points where y is equal to 1 are easy. So let's look at if we can find a place on our red graph where the y value is 1. Can you see that the y value is 1 right there on my red graph? 1 times anything is itself. So my green graph, here in this case it's going to be 1 times a negative 1. Well, my green graph has to be exactly at negative 1. We can do the same thing where the blue graph is 1. And I'm going to take, I'm going to take this point first. Because where that blue graph is 1, if I multiply it by the red graph, my green graph is going to be exactly right on my red graph at that point. Because 1 times anything would stay the same. What about that point? Because my blue graph is 1, and my red graph is, there is no red graph. What is 1 times does not exist? It does not exist, right? Error. So we need, maybe we want to make a point here to write this down. Well, that might look like 0 factorial. Better not do that. So because we need the graphs, the y values for both graphs, the domain of our green function is going to be x is bigger than or equal to 0, because you have to look at the domains of both the blue graph, right? The blue graph's domain, g of x, is everything. The red graph's domain is bigger than or equal to 0, so our green graph's domain is bigger than or equal to 0. So one of the things that you can do is points where y is equal to 0 are easy. Points where y are equal to 1 are fairly easy, a little bit more complicated. We found out that our y values have to exist for both graphs. The domain of, that's a very fancy of. That is also fancy of, but a little bit more legible. So we could take other points if we wanted to. We could say, ooh, here my y value is 2. On my blue graph, my y value is 8. 2 times 8, I should get 16. Okay, that's off my graph. Maybe I want to find, are there other points where I can put things together? And afterwards, you sort of connect the points that you have and draw your graph.
Would we have to keep going in the other direction too to see if it's, or can you just do that? Because it looks like a parabola, so you have to find a point to ensure that it goes.
That it keeps going up. Okay. a couple of things to consider as well with the multiplying ones, okay? First of all, you do some mental math with positives and negatives. You know that when you multiply a negative times a negative, it'll be positive. A positive times a negative will be negative, and a positive times a positive will be positive. So we can see, does it make sense that this section here is negative because my blue graph is negative and my red graph is positive. Then afterwards, this next section going up is always positive because both my blue graph and my red graph are positive. How do I know my green graph goes up forever? Well, my blue graph is getting bigger, my red graph is getting bigger, and a bigger times a bigger number will be bigger again. So multiplying a little bit more complicated just because multiplying is more complicated than adding and subtracting. It's a little bit harder to do our mental math. And the one thing about combining functions this way is our final graphs don't necessarily look like anything that we would expect. The adding and subtracting seems fairly straightforward, but the multiplying could look like a different graph altogether. And finally, part D, what haven't we done yet? Dividing. Right? The rule stays the same. We divide the y values just like we've added y values, subtracted y values, and multiplied y values. In this case, we want to draw our green graph as our red graph divided by our blue graph. So we'll take the values where our red graph, the y values of our red graph, and divide them by the y values of our blue graph. Okay, 0 becomes important. Okay, again, right? 0 is important when the numerator is 0. It equals 0, right? If you have 0 on the top of a fraction, 0 divided by 5 is 0, 0 divided by 7 is 0, 0 divided by anything except for 0 is 0. So do we have any situations where our red graph is 0? Yes. Right there. Okay? What happens when the denominator is 0? We get an error. Not possible. What happens in a graph when you divide by 0? What have we had? Asymptotes. We have a possibility of asymptotes or holes. And I'm just going to write 0 divided by 0 in brackets there. Because in order to have a hole, you need to have a factor the same that cancels out. And so in this graph, my blue graph is 0 at 3, and it's 0 at -3. Does it make sense that if you factored that blue graph, you would have an x plus 3 and an x minus 3 as factors in order for that to work out perfectly? Because that's how you would get those to be zeros. In this case, we are going to have asymptotes, so take out your red pens. and draw in your asymptotes at x equals 3 and negative 3. They're asymptotes because we can't divide by 0. And so our blue graph is on the bottom, and we would be dividing by 0. When you divide by 0, two things happen. Either you get asymptotes in your graph, or you get holes in your graph. You will, for the majority of times, you will get asymptotes. The only times you will get a hole is when both the red graph and the blue graph are 0 at the same place. Because that would mean that both of them have the same factor. And when factors cancel out, that's when we got a hole. So one of the things you're going to do is zeros first when dividing. You're going to find out, where's my graph still going to be 0? That's the green point so far. And where am I going to have asymptotes or holes? Then after you've done that, what are some other things that are easy to divide? It's easy to divide by 1, right? So when the denominator is 1, that's easy. So if we can find out, when is my blue graph 1? My blue graph is 1 here, and my blue graph is 1 there. What happens when you divide by 1? Nothing. So my green graph at those points is going to be exactly the same, because if I do red divided by blue, it's going to stay the same. Red divided by blue, it's going to stay the same. So when the denominator is 1, it's going to be easy. Okay? Another thing that's easy is when the graphs intersect. What happens when the red graph and the blue graph intersect? What do you know about their y values? What's that? I'm going off the y-axis for the 1, yes, because it's when the y values, again, we're always talking about y values. What do? We divide y values. So we're always looking at our y values when our y values are 1. When the graphs intersect, what do we know about the y values at those points? They're the same. So we can write that. And mathematically, if the y values are the same and you're dividing them, what do you get? 1. So if I look on my graph, where are my y values the same? Right here. My graphs intersect. So my green graph is going to be at 1 there and 1 there. So taking the easy points so far, okay, we've got a bunch of points given to us. We've got some asymptotes. You might be able to say, ooh, it sure looks like this is what's going to happen. Because graphs approach asymptotes. Other things that you're going to use in dividing. If you have a positive number divided by a positive number, you will get a positive number. Does that make sense? So this section that I graphed so far, both the red graph and the blue graph are positive. So my final graph has to be positive as well. what's going to happen in my other sections? Well, here I have a red point at 4. My blue graph, I don't even know where it's going to be, somewhere down here. If I did the red divided by the blue, 4 divided by negative something, will my answer be positive or negative? It's going to be negative. So I don't know exactly where this is going to be. Does it look like my blue value or my red value is going to be bigger? It looks like the blue value goes down faster than the red value goes up. So I would say that my blue point is bigger than my red point, and I'm doing red divided by blue. It's going to be negative. Maybe I'll estimate it to be negative 1/2. I have to make a decision what I think this graph is going to do in this section to the right of the asymptote. And here, there's not a lot of rules to follow other than thinking about it logically. I know that my green graph in that section to the right of x equals 3 is always going to be negative. Since it's always going to be negative and it has to approach the asymptote, it's got to go down towards the asymptote there. It can't go up towards the asymptote, because then my values would become positive. I also look at my blue graph and my red graph. And looking at the two of them, I'm going to say that it looks like my blue graph gets bigger faster than my red graph. As a result, my green graph is going to approach 0 here. It's got to stay negative, but it's going to approach 0. And so this graph also has an asymptote at y equals 0. We could do the same thing to the left of negative 3 and get a similar result.
So it just has to be negative because you're dividing by negative?
It has to be negative because one of the values is positive, one of them is negative, right? And so if you have a positive number divided by a negative number, you're going to get a negative number. Okay? Some other things that you can use in this unit that will be really helpful is stuff that we did in Chapter 2. Chapter 2 is when we did all the rational graphs divided by each other. If you look at this graph, can you see that your red graph, well, it's an absolute value graph. But if we look at just the right-hand side, the red graph looks like a line. What does the blue graph look like? A parabola. If you took any line and divided it by any parabola and think about what happened in Chapter 2, what happens when the degree is bigger in your denominator? You always had an asymptote at 0. I like that because that's one of those things where they're like, yes, Mr. JR, I remember that after you told me, but I did not remember that before. But this comes back and connects to that unit as well. So you can use what you learned in that unit to also help you realize that there's going to be an asymptote at y equals 0 in this situation.